these multi-cores also not very nice, because inside this multi-core we have again these logic, this Tomasulo logic, this out-of-order execution logic, which drops down my usage efficiency of the transistors. So we have to think in transistors, or in chip size, in die size. That's basically what we're going to do. We're paying die size when we're buying a transistor, because it costs nothing to put, buying a processor, sorry. It costs nothing to put transistors on a die, but the die size costs. And yeah, what are they going to do? Now, the easy approach is multi-core. Yeah, that's, everybody does this, Intel, AMD, of course AMD first, then Intel. The second approach is vector processing. I think that's a very old thing. Vector processing was done by Cray, and I think that the first Cray was a vector processor. And it looks a little bit like the cell processor, if we look at it, but the cell processor takes it to the next level. So we have vector units which are going to accelerate our code, but we have to care for programming them. And yeah, basically the same thing as SIMD. We all know that's being in the commercials since 2 years. The LTVAC or MMX or SSE or SSE2 or SSE3 or some more SSE. So we are extending the command set, so the instruction set, the ISA instruction set architecture, with new instructions which are vectorizing our code. So again, the programmer has to find it. There's currently no real compiler which, okay, they're trying to develop some, but I didn't see a really good compiler which really finds vectorizable code in some random program. They're just these mathematical programs which are very easy to randomize, to vectorize, because because they are not random. They're like do loops, and yeah, it's very easy to find a vector inside a do loop because it's just a do loop. We can introduce more registers. That's also very interesting. So if I have more registers, I have basically a bigger working set. The processor is working on registers, at least in a load store, in a clean load store architecture. And I think most of our processors, our current processors, are load store architectures. They seem that they're x86, these ugly, you can operate in memory and you can operate on anything else. But yeah, they're translating it. So they have 2 layers, and they have an outer layer and then an inner layer, which is a RISC, and the outer layer is just receiving all these high-level x86 commands, translating it into multiple small commands and operating on it on internal registers and something like this. But you have to ask Intel or AMD for this, I don't know. We can introduce explicit SRAM, which is basically the same as more registers, but it's cheaper. So SRAM is not, we can introduce bigger amounts of SRAM. We'll see this at the cell processor. They have a big amount of SRAM, but only, okay, very small amount. It's not small, we'll see. Yeah. Yes, but it's explicit cache. So it's not, cache is something you don't see. Bless you. Cache is something you don't see. It's like it's just working magically for you. It's finding your access. It's using your locality principle for you without managing it or without mentioning it. But this explicit SRAM is just like a scratch board for you, a scratch space where you can program, which you can using by programming, or which the compiler can use. Yes, yes. Okay, and then we can add GPU parallelism. So we all know that the GPUs, today's GPUs are highly parallel, because a task of rendering an image is highly parallel, it's implicit. So, from x86 to the future, that's a question mark, because I'm not sure about this. But I think the RISC design is a way to go, because it's easy and it can be very fast. We can clock RISC processors up to several gigahertz, up to 10 gigahertz with no problems, because they're very easy. The CISC design is not that way, but I'm not sure. It depends. The RISC design just moves the complexity into the upper layer, into the software. We have to care about programming it, and the CISC design just tries to manage everything in hardware. So that's a basic basic difference. We are going to have in-order CPUs because this out-of-order principle is quite nice to find instruction-level parallelism, but we pay a high price for this. We need all this Tomasulo logic, reservation stations, and all this additional hardware we don't need without it. And actually, Intel did a very interesting, I don't want to say experiment, but yes, this Itanium architecture, you all know. Maybe somebody thinks, or maybe most of you think that it's dead, but I don't think so, because it's a very interesting architecture. The only mistake they did was to introduce it without a background. So the cell is the same. We are going a new way. We are destroying most of the compatibility and going a new way, in a new direction, but we have a background, or they have a background, IBM, Sony, and Toshiba, because they have PlayStation. That's what it's going about, and that's going to be a big success, because yeah, many people will buy PlayStation, but how many people will buy servers with Itanium processors? Okay, he said that it's HPUX is available for Itanium, and yeah, that's going to be better, I think. But we'll see. I'm not sure, because it's just too expensive, this processor, yet. And okay, then we have a system-on-chip design, which everybody's going a system-on-chip design, because basically 2 cores on a single chip is a system-on-chip. And then we can support heterogeneous multiprocessing. Okay, but I have to go on that you can see the demonstration later on. The cell architecture. First patented by Ken Kutaragi in 1999. It's I think the CEO of Sony, and he has a vision. That's a very visionary vision. It's very far away, and just look at this. You have different devices, and you have hardware cells, which is basically a processor processing a software cell. And a software cell is just like a small task. So you want to do something, you pack it into a small packet and send it somewhere in the net, and it will come back processed for you. And yeah, so floating software cells, I think that's written in the patent. And yeah, that's what's on this slide. But we're not in this way, not yet. We'll see if this will come. But maybe, yes, these software cells will be controlled by the government or something, and we are able to process them by ourselves. The cell processor is actually a heterogeneous multiprocessor consisting of 9 cores. And these 9 cores have many abbreviations. So I just want to introduce these abbreviations that you can follow me later on, because it's going to be very abbreviative. The SPU is the synergistic processing unit. So you all know what synergistic means, I think. It's a very funny thing, but I don't know why they call it synergistic. But the second thing is the memory flow controller. So an SPU plus a memory flow controller is a SPE. It's a synergistic processing element. That's basically 8 of these 9 cores. And then we have an additional power processing element called PPE. That's the old legacy thing inside this processor, which keeps up compatibility to the outer world. So it's just running anything. Every program which is running on a PPC 970 is running on a cell processor without any change, because it has this power processing element on it, and it just can process the application as normal. And yeah, put everything together, we have a cell processor, and these are 9 full-blown CPUs. So we buy 1 processor, and we have 9 CPUs, and this processor is not going to be very expensive. So basically, I think this PlayStation will be the cheapest thing to buy a cell processor, but I'll come to this later. Okay, all these elements are connected with the element interconnection bus, and of course, they have an I/O connection to the outer world, or to other cell processors, or to anything else, just to submit, for example, these software cells to other cell processors. And we have a memory interface controller, which of course is interfacing to XDR, because Toshiba. And unfortunately we have hardware DRM, and we'll see how bad it's going to be. I hope we can switch it off. I'm not sure, but because Sony is inside, and I think if Sony is able to put a hardware rootkit into the cell processor, they are going to do it, and that's maybe this hardware DRM, and so I'm not sure. There's also another very funny thing about Sony and the PlayStation, but I'll tell you later. And the interrupt controller basically routes all interrupts just to the PPE, because the PPE is supposed to do all operating system tasks. So, for example, if you're moving your mouse, the PPE is processing it. It's not processed by any SPU. Effective, it's a network on chip, of course. And yeah, we have this number, 256 gigaflops inside a processor. But yeah, we'll come to this later also. Okay, that's how IBM, so source and copyright IBM, sees the cell processor. Many abbreviations, but basically what I told you. We have the element interconnection bus, interconnecting everything, power processing element, memory controller, bus interface controller, the SPU or the SPE. So then we have a synergistic execution unit, of course everything is synergistic, and a local storage. So there's the first prototype. The first prototype was, of course, produced by IBM, or inside this alliance between Sony, Toshiba, and IBM. It's a 90 nanometer silicon on insulator and has 8 copper layers. It's reminding me of the Opteron, I don't know why. And 241 million transistors and a very small die size. We see 235 square millimeters. And it takes only 60 to 80 watts. And that's amazing, I think, for this power we can get out of it, for this calculation power. And they only enabled 6 to 7 SPEs, but okay, that's going to be normal at the beginning of the production process, because the yield would be very low if we would enable all SPEs. It's just like the like Intel does like every processor vendor does, for example. If something in the cache is broken, just switch it off and sell it at a cheaper price. So it's going to be a Celeron processor if something in the cache is broken. And yeah, that's what they do. And that's also what maybe happens to the PlayStation, but we'll see. And it supports IBM virtualization technology. A very interesting approach. So we can run multiple operating systems on it simultaneously. Like, you know, maybe Xen, and it's Xen in hardware, or VMware in hardware. And yeah, it's operated at 1.1 volt, and it's able to achieve clock frequencies higher than 4 gigahertz, so the prototypic implementation. Okay, now I'm coming to the interesting thing. That's a floor plan of the cell processor. I think it's also copyrighted by IBM or somebody, but I found it on the net. We have the first thing, that's the PPE. That's the PPE, and that's the layer 2 cache. So we see layer 2 cache is quite big. And we have to remember, every square millimeter on this floor plan costs money. So it's not about transistors or something, it's about square millimeters. Okay, that's just a block diagram. And to say something about the PPE, it's not very interesting because it's a PowerPC compatible and runs every PowerPC code. It's a dual-threaded 64-bit power architecture, of course. Dual-threaded, it's this SMT simultaneous multi-threading is like the Intel, how's it called, hyper-threading. So it's some virtual parallelism inside the processor. It has, of course, the vectorized multimedia extensions and is a simple architecture. That's the biggest difference to the power processors, for example, Power 4 or Power 5, because it supports only in-order execution. Why this? We have a very high clock frequency, so we are running these chips at 4 gigahertz, and we can't. And everything is running at 4 gigahertz: the PPE, the SPEs, the bus, and yeah. So we need a very simple architecture with a very deep pipeline. So not as deep as the Intel processor, but still 20 pipeline stages is quite, yeah. Yeah, you told me that you did it as 30.